Hello, my name is Fatih Furkan Erkeç and I'm going to do practice lab neural networks for handwritten digit recognition binary for machine learning class assignment. And let's start with run packages. In course 1 we implement logistic regression. The dataset, we will start by loading the dataset in this task. We use the load data function. It loads the data into variables x and y. In here we print the variables and see the elements of the variables x and y. Then check the dimension of the variables, and here is our printing result. Visualizing the data, we will begin by visualizing a subset of training dataset. In the cell below, the code randomly selects 64 row from X, maps each row back to a 20 pixel by 20 pixel grayscale image and displays the images together. The label for each image displayed above the image. So here is numbers. Yes. The model representation. The neural network you will use in this assignment is shown in the figure below. This has three dense layers with sigmoid activations. Recall that our inputs are pixel values of digit images. Since the images are size of 20 by 20, this gives us 40 inputs. And the parameters have dimensions that are sized for a neural network with 25 units in layer 1, 15 units in layer 2, and 1 output in layer 3. Recall that the dimensions of the parameters are determined as follows in the info here, explanation here. For example, shapes of W and B are the shape of W1 is 400, comma 25, and shape of B1 is 25. So the W will be of dimension S in times S out. B will be a vector with S out elements. So we have a product of S in S out. Like this. TensorFlow model implementation. Exercise 1. Below, using Keras sequential model and dense layer with sigmoid activation to construct the network described above. Okay. Let's see. We'll start coding here. Here Keras and layers dense 25 activation sigmoid. Okay, let's copy and paste this, and then we will change these values by this, as we can see in here. Oh, yeah, we forgot the commas in here. Okay, so we see in here it's works good. Okay, yeah, some hints in here and our expected output in here. Now test passed. The parameter counts shown in summary correspond weight and bias arrays shown below. Let's run these. We print the weights, and as we can see, our expected output and our output are same. In here, we define a loss function, run gradient descent to fit the weights of the model of the training data. And to run model on an example to make predict on, use keras predict. The input to predict is an array, so the single example is reshaped to be two-dimensional. The output of the model is interpreted as a probability in the first example. The input is 0. The model predicts the probability that the input is 1 is nearly 0. In the second example, input is a 1. The model predicts the probability that the input is a 1 is near the 1. As in the case of logistic regression, the probability is compared to a threshold to make a final prediction. Let's compare the predictions versus labels for a random sample of 64 digits. This takes a moment to run. Okay, our output in here. NumPy implementation. As described in the lecture, it's possible to build your own dance layer using NumPy. This can be utilized to build a multi-layer network, as we can see in here. In exercise 2, build a dance layer subroutine. The example in the lecture utilized for loop to visit each unit j in the layer and perform the dot product of the weights for that unit, and sum the bias for the units bj to form z. An activation function gz is applied to that result. This section will not utilize for some of the matrix operations described in the optional lectures. These will be explored in a later section. Okay, here we will write a for loop, and let's try to write in here for e range, e in range of units, w is equals to uppercase w, and uh, e equals to that function w a underscore in plus bi a underscore out I equal to gz, and that's it. Let's run this code. Oh, we forgot to do this, I think. No, I mean not here. Okay, our output is same as the expected output. So let's run this, and the following cell builds a three-layer neural network utilizing my dance subroutine above. We can copy trained weights and biased from TensorFlow. Bias from TensorFlow. Run the following cell to see predictions from both the NumPy model and TensorFlow model. This takes a moment to run. Vectorized NumPy model implementation. The optional lectures describe the vector and matrix operations that can be used to speed the calculations. Below describes a layer operation that computes the output for all units in a layer on given input example. We can demonstrate this using these examples x and w1 b1 parameters above. We use NumPy matmultiply to perform the matrix multiply. Note the dimensions of x and w must be compatible as shown in the diagram above. Okay, we have vectorized NumPy model implementation here, and exercise 3. Below components and new mydance underscore v subroutine that performs the layer calculations for a matrix of examples that will utilize MP math mode. This function is not created, it's because okay. Okay, a out is equal to g combine math multiply a m and w plus b. Okay, as you can see, we have true output, the expected output. We have the info in here, hint in here, and the code in here. Okay, the old test is passed. We'll apply a threshold of 0.5 as before, but all predictions at once. Run the following cell to C predictions. This will take some moment to run. You can see how one is one of them misclassified images look. I couldn't see the misclassified, which let me try it again. I couldn't see that 0 again. Maybe it was about the samples that selects. I think it's about that. And if we select this 0, we should 0 and 1, but we can't select it for after several runs. For that reason I couldn't show it, but I think we did it right. So you have successfully built and utilized the neural network. Here we have a NumPy broadcasting tutorial, which is optional, and we utilize an NumPy broadcasting to expand the vector b z equals w plus b, and xw is a matrix operation with dimensions mj1, j1, j2, which results in a matrix with dimension mj2. To that we add a vector b with dimension 1j. E must be expanded to be a mj2 matrix for this element-wise operation to make sense. This operation is accomplished for you by NumPy broadcasting. Okay. When operating on two arrays, NumPy compares their shapes element-wise. It starts with the trailing dimensions and works its way left. Two dimensions are compatible when they're equal or one of them is 1. If these conditions are not met, a value error. Operands could not be broadcast together. Exception is thrown. So here is the example. This graphic below describe expanding dimensions. Okay, we should try to guess the size of the implementations. And in here, is 5, 1, 2, 3, reshape plus b and 8 times b, and there's again shape is 3 to 1 and 5, 10, 15, I think, and in here whole column elements wise operations. In here we a plus b one by one and 1 by 2, 1 by 3, and 2 by 1, 2 by 2, 2 by 3, 3 by 1, 3 by 2, 3 by 3, and then same operations for 4, as we can see here. These for the ones, these for the twos, and fours. Okay. So that's it for this assignment. Thank you for watching. Have a nice day.